Hello, my Algebra 2 people. This is Mr. Hotard. This lesson today, we have two parts to it. The first part, we're going to be working with polynomial terminology. We're going to be identifying whether something is a polynomial. We're going to be identifying the degree, writing in standard form, and classifying it by its degree, type, and leading coefficient. So first of all, what is a polynomial? All right, polynomials are just expressions where all the variables have exponents that are whole numbers, that are basically all of the exponents in the problem. They cannot be negative, they cannot be fractions, they cannot be decimals. You can have fractions and decimals and negatives in the problem, just not in the exponent. So for example, if you look at down at the bottom, this first one right here, if you look at all the exponents, this one's got a 1, that's a 3, a 2. There are no negatives or decimals or fraction exponents. All right, there are negatives in the problem, but not in the exponent. So yes, this one is a polynomial. So there are actually, if you look at this, there are two of these that are not polynomials. All right, all of them are except for two of them. Do you see them? Here's one. All right, this one's got a negative exponent, so this one is not a polynomial. And there's actually another one. This one's not as obvious. It's the last one, because this minus 5 over x, since the x is on bottom, this is like the same thing as saying negative 5x to the negative 1. When the x is on bottom, that's like a negative exponent. So no, that one is not a polynomial, but all these others are. Okay, now a little bit of terminology we need to discuss. Okay, so first of all, types of polynomials, right here. Some of these words you should have seen before. Constant, that's, for example, that would be like y equals 5, just y equals a number. That would be a constant polynomial. Linear, you've seen linear before. That's like mx plus b. So for example, y equals 2x plus 1. That would be a linear function, a linear polynomial. Quadratic, what does the problem have to be quadratic? Got to have an x squared. So something like y equals 3x squared minus 4x plus 6. That would be an example of quadratic. So what do you think cubic would have to have? It would have to have an x to the third. Something like y equals 8x cubed plus 2x squared minus 7x plus 1. Something like that would be cubic. Now the next one, quartic. You're looking at this pattern, what do you think quartic has to have? It has to have an x to the fourth. So a quartic polynomial would be something where the biggest exponent is 4. Y equals something like 9x to the fourth minus 5. And there's actually one more I meant to put on this list, quintic. Quintic is when you have x to the fifth, something like y equals 12x to the fifth minus 7x to the fourth. Now, why do we call them these names? They get these names based on the degree. The degree of a polynomial is the highest exponent on the variables, just the biggest exponent in the problem. All right, so if you look down at the quintic one, what's the degree of that? It's 5. The biggest exponent is 5. Degree of quartic is 4. Degree if it's cubic, that's 3. Degree if it's quadratic, that's 2. What's the degree if it's linear? It's 1. That's like 2x to the 1 power right there. So the degree would be 1. Now based on this pattern, what must the degree be if it's constant? You're looking at 5, 4, 3, 2, 1. It should be 0. All right, this, when it's just y equals a number, this is like saying y equals 5x to the 0 power. All right, it's like having x to the 0. That's why the degree is 0. And then one last thing, you notice all these problems, when I wrote them out, I wrote them biggest to smallest exponent. I wrote them in what's called standard form. Standard form of a polynomial, that's just where the terms are written in descending order of the exponents, from biggest exponent to smallest exponent, ending with the constant term, the thing without an exponent. So if you look down at the bottom, I want you to take a moment right now. We've already decided if they're polynomials or not. If the answer was yes, I want you to rewrite it in standard form and then tell me its degree. All right, that's the biggest exponent. Its type. And then leading coefficient, that's just the front number after you write it in standard form. Did you do it? I sure hope you did. Okay, let's check our answers. So again, you had to write it in standard form first before you can answer these questions. So the first one going to be 5x to the third minus 6x squared minus 3x plus 2. The degree is 3, biggest exponent. And if the degree is 3, what type is it? It's cubic. And then the leading coefficient, the LC, it's 5. That's the front number after you write it in standard form. Second problem, going to be 6x to the fourth minus 4x to the third plus 1/2x squared plus 3x minus 1. Putting it in order, degree is 4. It is quartic because the degree is 4, and leading coefficient is 6. The third one was not a polynomial. The fourth one, write it in order, 13x squared minus 12x plus square root of 3. Degree is 2, that makes it quadratic. The leading coefficient is 13. And then the last one, because the very last one's not a polynomial, but this one, going to be negative square root of 7, x to the 4th, plus 8x to the 3rd, plus 5/3 x squared plus x minus a half. Biggest exponent, the degree is 4. That makes it quartic. And the leading coefficient is that front number. It's negative square root of 7. All right, so that's polynomial terminology. Pretty easy, but you need to know that stuff in order to be able to do what's coming up next. So second half of this video, we're going to be looking at one specific part of graphing these polynomials. We're going to be looking at something called end behavior. All right, end behavior is basically what the graphs are doing at the ends of the graph. So we're going to start with something you know. F of x or y equals x squared. What shape does that make when you graph it? It's a parabola. All right, start at 0, 0, and go up both ways. It would look like that. Now if it has a negative x squared, that's also a parabola, but how's that parabola different? It's reflected, it's flipped over. So that would be a parabola open and down, going down on both ends. So let's just draw the graphs and then we'll come back and talk about what this stuff means. So the others, x to the 3rd. Do you remember what shape x to the 3rd looks like? It's kind of like a squiggle. All right, it goes through 0, 0. All right, it looks kind of like this. It starts down here, goes through -1, -1, and then kind of curves and curves again. Does that. That's x to the 3rd. So what would negative x to the 3rd look like? It'd be that flipped upside down. It would start up here at the top, kind of curve. It's hard to draw. Go through the 0, 0, and then curve again, and down at the bottom. Okay, so when we're talking about end behavior of these graphs, we're looking at what is the graph doing at the ends, all right, on both ends. Like if you look at, going back to number 1, both ends of this graph are going which way? Up or down? They're both going up. So to describe this end behavior using, this is called arrow notation. Basically this is saying as x goes to negative infinity, as the x numbers, here's the x numbers, as they go to the negatives, that means as we go to the left, is this graph going up to positive infinity or down to negative infinity? It's going up, so I would put a positive infinity in that blank. Now as x goes to positive infinity, that means as I go to the right. Basically if you go to negative infinity, you're going to the left. If you're going to positive infinity, you're going to the right. As x goes to positive infinity, as I'm moving to the right, is this graph going up or down? It's going up. So in problem number 2, all right, this one, as I go to negative infinity, as I go to the left, which way is that graph going, up or down? It's going down to negative infinity, so I would have negative infinity here. And as I go to the right, it's also going down. I'd have another negative infinity. So now I want you to see if you can fill in the blanks of the other two. Did you do it? I sure hope so. So let's check to see if you did it right. As you go to the left, is this graph going up or down? It's going down. So as you go to the left, as x goes to negative infinity, that graph f of x going down to negative infinity. As you go into the right, it's going up to positive infinity. The last one should be the exact opposite of that. All right. As you go into the left, this is going up to positive infinity. As you go into the right, this polynomial is going down to negative infinity. So you're just filling in either infinity or negative infinity. Whenever it's asking about end behavior of the graph, you're going to write this out. It's just, this is either going to be a positive or a negative infinity. Now, to summarize this, right, you're not, in order to identify the end behavior for a specific problem, like an example of this one, I don't have to necessarily graph that on my calculator. If you can remember these 4 graphs, you can answer end behavior for any polynomial, any problem, because it follows these rules not just for x squared, it follows the same end behavior rules for any even exponent and then any odd exponent. So basically, if your degree, now remember, what's degree mean? The biggest exponent. If your degree is even, 2, 4, 6, 8, any kind of even number, and the leading coefficient, remember that's the front number in the problem, if it's a positive, that means both ends of the graph are going up. There might be some other crazy stuff in between them, but the ends of the graph are both going to be going up. All right, if you have an even exponent, like x squared, x to the fourth, and there's a negative in front, both ends of the graph are going to be going down. All right, if there's an odd exponent, like this one, with a positive in the front, what are the ends of the graph going to be doing? Are they going the same way? Nope. It's going to start down at the bottom, and it's going to end up at the top. There might be some crazy little squiggles in between them, but that's what the ends of the graph are going to look like. And then if you have an odd exponent with a negative leading coefficient, a negative in the front, it's going to be the exact opposite of that. It's going to start at the top, end at the bottom. If you can remember these four things, even exponents, just like x squared. It's either both going up or both going down, whether it's positive or negative. Odd exponent, think of it as like the slope. Positive slope going to start at the bottom, end at the top. And negative slope, negative leading coefficient, going to start at the top, end at the bottom. And so, if you look at this last example right here, if I want to describe the end behavior of this, I don't need to graph this in my calculator. I just need two things. I need the degree. What's the biggest exponent here? It's 4. Now, is 4 an even or an odd number? It's even. So it's an even exponent, even degree, and look at the leading coefficient. All right, what do you notice in the front? Is there a positive or a negative? I'm seeing a negative in the front. I've got an even degree, a negative in the front, negative leading coefficient. So I know the ends of the graph are going to look like this. I know the ends of the graph are going to both be going down. Now that's not the answer. This is what I used to find the answer. The answer I'm going to write like this. All right, if both ends are going down, I would write this out. I would say for my end behavior, f of x approaches negative infinity as x approaches negative infinity, and f of x approaches negative infinity as x approaches positive infinity. Now, where did I get that? I got it from this. All right, it's the same thing right here. You're basically going to have one of these four answers every time for end behavior, all right, just based on the biggest exponent and the front number after you put it in standard form. Now, if this was not written in order, you had to put it in order first. Okay, I hope that was helpful. This is Mr. Hotard out.